Hello and welcome to another video in this series as we journey from the very simple primes to the foothills of the Riemann hypothesis. Today's video should be quite short but quite exciting. We're going to continue what we were doing previously, which is to explore the Riemann Zeta function, the series that we developed that we know is intimately linked to the prime numbers through the Euler product formula. Certainly go back and refresh yourselves on previous videos. And the last time we made a significant jump from looking at the Riemann Zeta function along the real line, the normal numbers, to the complex plane. So its parameter s, we upgraded it in some sense from being a number which could be 1.5, 0.2, 9.8 to a complex number which is two-dimensional. And the output of that function is also a complex number, and we try to visualize it by taking its magnitude and taking its log as well, just to kind of scale it down a little bit. And we saw some interesting features. And here's another quick view of it as a reminder. And you can see there's a point where it gets larger and larger and larger, and that corresponds to the value s equals 1 with no imaginary part, and that's the harmonic series. So we know there's a discontinuity, a singularity, as it approaches s equals 1. We know that, and we worked out that this Riemann Zeta series is valid, it converges for sigma, the real part of s, more than 1. And we showed that if it was less than 1, then it doesn't converge. So that series is only valid for sigma more than 1. But what we also saw when we looked closely was hints that the function might have been artificially cut off. So this is the plot of the same function, and as you can see, if we zoom in a little bit, you can see that these iso lines, the lines along places where the height is the same, like a map in a way, of mountains, it looks artificially cut off. It looks like there's no reason why, if we're staying at this height, say 100 meters above sea level, we keep walking along that height, it suddenly stops. That artificial cutoff, that sort of discontinuity, is not what we expect of well-behaved normal functions. I mean, there are mathematical functions that do that, but it would be an unpleasant surprise if that was the case here. So there's a suggestion or a hint that it really does continue. So we're going to explore that a little bit more today. It's actually really simple. The maths that we'll do today, it's surprisingly simple, but the results will be quite profound. So before we even think about extending that function in some way, we should talk a little bit about what that really means. What does it mean? Is it a valid thing to do? The maths seem to tell us that it's only valid for sigma more than 1, the half plane to the right of that sigma equals 1. Surely it's invalid to even think about extending it. So let's look at a simpler problem, a simpler bit of maths, and understand it's there, the concept of extension, and then come back to the Riemann Zeta function. So here we've got a Taylor series expansion of 1 minus x and then the reciprocal of that. That's a very common thing to do at school. It's most people know it by heart, but if you don't, it's kind of easy to work out as well. There's a very standard method for working out Taylor series, and that's if you need a refresher, there's lots of easy guides for doing that. But this is the expansion, the power series expansion of this function, and this is developed around x equals 0. Now, when you work with Taylor series, you have to be conscious of where they converge and where they don't converge. And again, this is stuff we do at school quite a lot, to the extent that we might even get a little bit bored of it. But this one converges in the region where x is between -1 and +1, when x is along the real line. So that's sometimes called the radius of convergence, even though it's a kind of a one-dimensional line. So, wait a second. This power series, this Taylor series, is valid for this domain, and yet the function is valid for all x, except maybe x is 1, where it becomes a singularity, becomes infinite, 1 minus 1, and 1 over that. 1 over 0 is undefined or infinite. So for x equals 2, this is certainly defined. 1 minus 2 is -1, and 1 over that is -1. But this series is only valid in a smaller domain, a subset. What's going on here? Is there a fundamental difference between these two things then? Is this somehow inferior? Is this somehow what's going on? Let's find out. So that series that we developed around 0 is just one representation of that function f. That function f being 1 over 1 minus x. It's just one representation, and it's valid for some of that function's domain. We can have different representations. We can have several. There can be more than one representation of f valid in different parts of its domain. Let's look at one example. This Taylor series is another one developed from the same function f, 1 over 1 minus x, but this time it's not developed around x is 0, it's developed around x is 3. And its region of convergence, its kind of radius of convergence, is between 1 and 5. So it's a different domain that it's valid for. So let's just look at this this function, this 1 over 1 minus x. There's no surprise what it looks like. And you can see at x equals 1, it kind of diverges. It's plus or minus infinity, it's not defined there. But you can see it's defined for every other x, as large or as small as we want. So that's the f. And when we look at the series that we developed around 0, the S0 series, its region of convergence is between -1 and +1, and this is calculated to, I think it's about 4 or 5 terms. The more terms we include in that series, the more closely it matches the actual green line, which is the function f. So it's an approximation, clearly, because we've chopped off terms. So the more terms we have, the closer it matches. But this is just to illustrate that it's there. And the other one that we did, S3, developed around 3, is valid between 1 and 5. And again, we've calculated it to, I think it was 5 terms if I remember correctly. So it's a fairly good match. But they're not the same. So what's going on? Well, the answer is that, and we've kind of said it already, that they are both those series, both represent f, but in different parts of its domain. So in some sense, f is the true function, and this series, S0 and S3, and maybe even S5, and any other one we want to develop, they are parts of the function in parts of its domain. That's the difference. And that's the important point which we need to take away here. There's a distinction between a function and then the series which represent it in different parts of its domain. So let's imagine we've got a function like this. there's a kind of a point where it's got a singularity, and that's the true f, and then we might have a series which represents this actual function. We might have a series which is valid between, say, it might be valid in this region. We might have another one that's valid in this region. We might have another one that's valid in this region. Just because of the way Taylor series work, the limits of the radius of convergence are decided by where the singularities are. But that's not the important point here. The important point is we can have a series, and then another series, and then another series, which are representing that function in different parts of its domain, and some of them can overlap. This one overlaps this one, and when we come back to our own example, we could have developed a series at 5 or 4 which would have overlapped this one but extended further, and that idea is called analytic continuation, when we extend the domain of a series so that it still represents the true function, some other true function, but in more of it. Great, so the main point that we've decided there, the main learning we've done, is there's a distinction between a true function and then series which represent it. So that leaves us with an interesting question. Perhaps the series that we've been so obsessed with, 1 over n to the s, the Riemann Zeta series, what if that series, which we know is important because it's connected to the primes using the Euler product formula, the Euler golden bridge, what if this series was only representing a more important function in a limited domain? What if this only gave us a partial view? And that's an intriguing possibility. All this time we've been exploring this function, this series, thinking of it as the function. You have to be careful now with some of the terminology, series and functions, so let's say that again. We've been exploring this series assuming it was the function that was of interest. We've been calling it the Riemann Zeta function. Which certainly is a series, is a Dirichlet series. What if this was giving us only a partial view of another function? And what if that other function was a better thing to explore because it might give us more insights into the prime numbers? That's an interesting step to take, and that's what we're going to do. In fact, what we're going to do today is just extend it by a little bit, and then in future, just because the maths gets a bit more involved, we'll extend it more. But the core ideas, the kind of the plain English ideas to take away are, number one, we've seen how series can provide only partial views of a greater function, and the idea we're taking forward now is this series providing us with a partial view of some other function? Then what is that other function? That's an exciting thing to kind of explore. So let's do that. And in fact, it's not difficult at all at the first kind of extension that we're going to do. So we're looking at something that looks slightly familiar. We've seen the series here, but you'll notice this time this isn't quite the zeta series that we were used to. This has got alternating minuses, so instead of plus 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 plus, it's 1 minus plus minus plus minus. And this is sometimes called the alternating zeta function, but it's also called the eta function, and that's the symbol for it. So the eta function is minus 1 raised to the power n plus 1, so that it alternates over the same old n to the s. Now, the convergence for this, the region of convergence, where does it converge, which S does it converge, you would expect intuitively that it converges over a larger domain than the plane zeta function. The plane zeta function we've seen now many times, and we proved it, that it converges for sigma, the real part of S, more than 1. This one you'd expect it to converge over a larger area than that one because it's got minuses, not just pluses. And in fact, we can work out that it converges for sigma more than 0, and that relies on the Dirichlet theory that we developed in one of our appendix videos, and you can read the blog as well. We won't go into all the detail because it is, the proofs of that are detailed, and they are in that video if you want to have a look. But the nice thing about that Dirichlet theory was that we could look at a series, look at the coefficients here, and if they were bounded, the sum of those coefficients, so -1 or 1 minus 1 plus 1 minus 1 plus 1 is bounded, it never grows to 2, for example. We could then automatically say that it converges for sigma more than 0. But as I said, if you're interested in the proof of that and the derivation of those criteria, do go and look at that video again and the associated blog. So the important point here is the zeta function converges for sigma more than 1. The eta function, the alternating one, converges for sigma more than 0. It's got a slightly bigger domain of convergence. That's exciting, that's interesting, that will be useful for us. So if we could express sigma in terms of this function, then we would have a new series for the thing that we're really chasing, the Riemann Zeta function. We would have a new series for it that has a slightly bigger domain. It then converges to the left of sigma equals 1 into up to sigma more than 0. So that's what we're going to try and do. We're going to try and express zeta in terms of eta, and it's not that difficult to do. In fact, looking at this, there's patterns we can exploit. They're similar already, and the algebra is really simple. So this is the normal zeta function. If we take the difference, zeta minus eta, you can see that the positive terms will cancel out. Let's look at that. 1, so the 1s will cancel out, the 3 and the 5 and the 6, so all the ones with the odd numbers at the bottom, they will all cancel out. But because there are minuses at this one, it'll become double. So we've got 1 plus 1 over 2 to the s, plus 1 over 3 to the s, plus 1 over 4 to the s, plus 1 over 5 to the s, plus 1 over 6 to the s, and that's our zeta. And then we've got our eta function, which is 1 minus 1 over 2 to the s, plus 1 over 3 to the s, minus 1 over 4 to the s, minus 1 over 5, oh that's plus 5 to the s, minus 1 over 6 to the s. So if we say zeta minus eta, so it's that minus that, which cancels, that minus that, which is negative, so it becomes 2 over 2 to the s. This cancels, this becomes 2 over 4 to the s, this cancels, the other one becomes 2 over 6 to the s, and so on. And you can see that there's a constant factor 2, so 2 over 1 over 2 to the s plus 1 over 4 to the s plus 1 over 6 to the s. And in fact that is zeta, as you'll see here. It's the zeta multiplied by 2 to the s at the bottom. So that's what we've just calculated, because they cancelled. We've taken the factor of 2 out, and then if we take a factor of 1 over 2 to the s out, we're back to zeta. That's a really nice, easy bit of algebra, nothing complicated. So that is just rewriting that to 1 minus s, because there's 2's there, and that's sigma. So we've got sigmas and we've got etas. That means we can isolate sigma quite easily. We can take it to one side, and that gives us a really nice formula for zeta in terms of eta. There's a factor here that's interesting, but now we've expressed zeta in terms of this eta here. Now the interesting thing here is that the right hand side eta is valid over sigma more than 0, because that's where this is valid. So in some sense we've expressed this function in another series which has a larger domain of convergence. So in some sense we've extended its domain. That's exciting. That's really interesting, and I can't wait to plot it to see what it looks like. But before we do, let's look at this this kind of factor, because it could be doing something interesting that we need to be careful with. So what do we mean by we need to be careful with? Well, does it become undefined at any point? Well, the top is just 1. The bottom, if this ever becomes 0, then this factor is undefined, so we need to be careful with that. So this is 0 when s is 1. So 1 minus 1 gives us 2 to the 0, which is 1. So 1 minus 1 becomes 1 over infinity, or it becomes undefined. So that s equals 1 is where this thing on the right, this whole thing, is not defined. It's called a singularity. And that's okay. That matches our understanding of the zeta function, because the zeta function at s equals 1, we know it diverges there. So as the zeta function before that we looked at, as it approaches from the right, s equals 1, we know it approaches the harmonic series which diverges. So that's good. That's compatible with our understanding. So that's interesting. But the main point, the key achievement, is we've found a function, a series, which is valid for sigma more than 0, and it agrees with zeta. So it's an extension. Fantastic. That's exciting. So if we visualize it now and look at it from sigma equals 0 onwards to the right, again it's got the familiar bits over here, but there's something else going on here. So we've got this singularity here, which is the divergence, but these, if you look at them closely, we'll look at the 3D plot as well, these are zeros. That's interesting. What does it, well, it's important when a complex function has zeros, but what does it mean in terms of prime numbers? What does it mean if this thing has got zeros? And if you play around yourself and you kind of plot this over a bigger range, you'll see more zeros further up and down, and they mirror each other actually, but they don't seem to stop. They kind of keep going up and up as the imaginary part of S gets larger and larger, and they also seem to lie on S equals a half, S equals real part half. They all seem to lie on that line. That's intriguing. That is interesting. What does that mean? Why do they appear to lie on the or do they lie on the line s equals half? Is it true for all the zeros? Actually, we've on our journey through all these videos that we've done so far, we've finally arrived at one way of expressing that very famous Riemann hypothesis that is, that is famous, that is considered extremely difficult, that no one has solved, that there's $1 million prize for. And one way of expressing that question, the problem, is, do all these zeros lie on s equals a half? So expressing the question isn't that difficult. Proving that they do is where the real difficulty is, and what the famous Riemann hypothesis is. And if you can do it, you can claim $1 million from the Clay Math Institute. So this is one of the famous Millennium Maths problems. What else can we say about this? Well, actually, again, it looks like we could continue even further to the left. Those ISO lines are cut off artificially again. It looks like a smoothly changing function has been cut off. That's again intriguing. Is there more to discover to the left of this? Can we extend it again? So that's something we can look at in future. But for now, let's ponder this idea of these zeros. So let's recap what we've done. We previously developed the Euler product formula. We called it the Golden Bridge, Euler's Golden Bridge, and it was 1 over n to the s sum equals 1 over 1 minus 1 over p to the s, and that's a product, that's an infinite product, and that's an infinite sum. And this connects all the primes to all the normal natural numbers. So this encodes information about all the primes. What we've now done is express this. We thought that was the zeta function previously. We then extended this to zeta, the Riemann Zeta function. We wrote it in terms of in a new series in terms of the eta function, eta of s. So it's 1 over 1 minus 2 to the 1 minus s. And this thing has a larger domain. This one was valid over sigma more than 1, and this one now is valid over sigma more than 0. And it's revealed, so that was valid there, and this one is valid over a larger domain. And with this one, we found zeros along what looks like s equals half. So that's a high level view of where we've come to. We have a connection between the primes and this series, which we've extended to this series and revealed zeros in this Riemann Zeta function, and we have clues that it could extend to the left of sigma equals 0. But these zeros, the zeros of a complex function, are always important, and our challenge is, well, how are they important? Do they have something to do with the primes? What is the connection? So that's exciting. So this kind of helicopter view of where we've got to, I think, is important, and it helps us steer our journey forward. So in the future videos along our journey, we will try to make clear the connection between these primes and these zeros, because the zeros of a complex function are important, and we'll kind of dig into why that is in future. And we've able for the first time to be able to express the famous Riemann hypothesis, the world famous problem. We haven't really explored all its dimensions and all its implications, and there's different ways of expressing it and talking about it, but this one is simple, and it's simply saying the hypothesis says the Riemann hypothesis says all these zeros lie on s equals a half. Prove it. So if we can prove that, we've done a huge service to mathematics. And that's kind of, we've struggled, we've not been able to do that in all the time that Bernard Riemann posed that as a hypothesis. So here's a 3D view of that extended function, and you can see we've extended it to the left now of that singularity at s equals 1. And just a reminder, this is plotting the absolute value of the complex function and then taking logs just to kind of accentuate its features. So although these look like they're going down towards minus infinity, they're actually going down to 0. So these are the zeros of this extended function. So let's summarize. We found zeros in this extended function, and they appear to be on the line s equals a half. And the question for us is, well, what does that mean? And is there a connection somehow between those zeros and the primes? Because the Riemann Zeta function is connected, it encodes the primes through the golden bridge, the Euler's product formula. What does it mean that those zeros are only on s equals a half, if that is true? What does it mean? What would it mean if they appeared elsewhere? If they're on s equals 1, for example, or even s equals 2? What does that mean? So these are questions we're going to dig into later, but it's worth setting out these kinds of signposts now. So we'll finish by looking at an animation of that function, just getting a rotating view just to see what it looks like. So fantastic, that's a real milestone on our journey. It's quite exciting actually. So I hope you'll stay with us as we continue our journey. If anything has been a little bit difficult to understand, or even something that you'd like to kind of talk about a bit more, or if you spotted a mistake that I've made, do get in touch, do comment on the videos, and we'll fix that. We're learning together. Fantastic. Well, we'll see you next time. Bye.